didn't forget anyone. And it gives me great pleasure to introduce our today's speaker, Professor Firash Hassawanieh. He's an associate professor of computational mathematics, science, and engineering at Michigan State University. He received his PhD from Duke University and a master's degree from University of Missouri. And then he held a tenure-track position at SUNY Polytechnic Institute prior to joining MSU. His research focuses on applied topology and dynamical systems with applications to mechanical and biological systems. He's particularly interested in time series analysis of complex systems, both deterministic and stochastic, whose models are either impossible or too difficult to derive.
Thank you, Ilya. Excuse me. Thank you, everybody. Can you hear me? Yeah, okay, wonderful, very good. I'm very happy to be here. I had very interesting discussions with lots of people today that will keep me thinking for a long time. And actually, I was thinking, when was the last time I was here? And I figured it out. I had the pleasure of giving a seminar in this series in the fall of 2019. So I'm very happy to be back to give another seminar on a different topic. So if you were here for the 2019 one, it's not going to be the same one. Okay, new stuff. The title of my talk is A Topological Approach for Data Assimilation, and I will explain what all of that means one by one. But first, I would like to acknowledge the sources of support that made this possible by sponsoring Max. Max is over there, and this is his work, so I'm presenting Max's work. Max graduated this week, right? Tuesday? Defend it in my mind. If you defend, you know. The rest is just signing, yes. And it gets better. He will be starting a postdoc position here in the summer, right, with Herbert, so. All right, so this is the outline of my talk. I said topological data assimilation. Topological comes from topological data analysis, which is a field of applied mathematics that has encountered a lot of successes. The flagship tool in TDA that has been used for a lot of applications, not the only one, but the most popular perhaps, is called persistent homology. So I'm going to talk about that. Then I'm going to talk about persistence optimization, time series forecasting, data assimilation, and then combine forecasting and data assimilation and persistence to have this new approach, topological data assimilation, and then I will show you some results. So let's start by talking about persistent homology. Imagine we have a space and we have some samples from that space. So in this case, I have this point cloud. These points could be sampled from manifold, for example. And I'm trying to use these samples to learn something about the shape of the underlying space, okay? So one thing I can do is I can introduce this thickening at each point in my point cloud. I can draw a disk of some radius r. For now, I'm going to fix it. So I have some fixed radius r. And every time I have two of these disks intersecting, I will connect the corresponding vertices via an edge. So now I have vertices and edges. And anytime I have three of them intersecting, I will put a triangle there, okay? And I'll fill it in. So now if you see this, I get some shape as described by these edges and triangles. This construction is called a Vietoris-Rips complex, okay? And this is the one I will be using. There are other types of filtrations that you can introduce or other types of complexes that you can use. But sticking with this one for now, for that fixed value of r, I see that there is a hole here that has not been filled in. So I have a loop in my shape, and all of these vertices and edges and triangle, they are all connected into one component. So in mathematics, we have homology, which is a tool that can tell us something about the shape. Homology, I have different dimensions of homology. Each one gives me information about some aspect of the shape. So zero-dimensional homology, H0, tells me how many connected components I have. In this snapshot, I have one. And H1 tells me how many loops I have in my shape. In this case, I have one, right? And you can go up higher in the dimensions of homology to H2 tells you something about the voids. So if I had a three-dimensional point cloud, I can look at voids and so on. Okay, so that's great, but that gives us a parameter that we need to choose, r. Which r should I choose? Because if I vary r, I will get different results. So the modern variant of homology called persistent homology says, let's look at all the R's. So we make R, which now I'm calling epsilon. Epsilon is just R in the other slide. That becomes my connectivity parameter or my scale parameter. And I vary that parameter from 0 until everything connects, okay? And then I observe what classes from my homology appear and disappear over these values of epsilon. So here I'm going to show you a video. Here's a point cloud. There you go. So I start increasing epsilon, and as I am increasing it, I get at this point where there is a hole that appears, and then it fills in. So this point here, the blue point, marks the epsilon value at which that hole got filled in. This axis, called the birth, tells me when that hole first appeared. And filled in means I have triangles that just cover that hole. Don't see it anymore. This diagram actually is two diagrams in one. It shows me the one-dimensional homology, persistent homology, or persistence, and the 0D. 0D is connected components. As you can see, all the 0D points in my persistence diagram are in one vertical line, because when I start this process called filtration, all the vertices are their own individual components. So I have as many of, they are all born together at time 0. And then they start connecting via edges as the filtration proceeds. And so they are all along this vertical line. There is one component at the end that goes to that dashed line marked by infinity. That's called the essential component, because at the end, I will have everything connect into one component. So that component just remains, does not die. Okay? So as I said, this is called a filtration as I build the sequence of simplicial complexes, all right, Vittori strips complexes. Each subsequent one, I have an inclusion process. Okay, so each subsequent one, each previous one is included in the subsequent one, and at the end, I have everything. I have all the triangles, I have all the edges. Okay. So that's persistence of point clouds in one video. So why do we care about persistence? So persistence has several advantages that I hope I will be able to convince you today of them. The first one is that it provides compressive summary of shape. I have a point cloud that has some loops, some loop in it, some circular structure. So all those points you see there in the point cloud, I can represent as one point of 1D persistence homology in my persistence diagram. So I go from a bigger collection of points into this compressive summary, where I can say a lot with just very little information summarized in the plot. So it has good representational abilities of shape in my data. Also, persistence is stable, which means that if my input data, in this case, that point cloud, if I have an input point cloud and I perturb the points, the persistence diagram from the original input data and the persistence diagram from the perturbed data will be close. Okay, if I have small perturbations, as you can see in that video. My point cloud is perturbed, my persistence diagram is perturbed, but it remains close to the original one. So there are theoretical proofs for that stability property. It's also noise robust. One of the nice things about persistence is that if you compute persistent homology for a point cloud or even a time series, I'm not going to talk about that. There are other flavors of persistence. Usually what you see happen is if I have a big structure in my space, like this one here, the circle, it shows up high above the diagonal. And all those small loops that show up because of the noise, they all kind of show up around the diagonal. Often, these points near the diagonal are attributed to noise. So if you're interested in the prominent features, you look at the ones far from the diagonal. But in some applications, they are important. Sometimes you do want the points near the diagonal. In today's talk, they show up as noise. Okay. Persistence is also conducive to machine learning. While I cannot use persistent diagrams as is in a machine learning algorithm, I can take them and vectorize them and then turn them into features that I can then feed through a machine learning framework. So here I'll just show you some applications of persistence. Because of that noise, topological noise filtering ability, it can be used for damping parameter estimation, for example. It was used in bifurcation detection. It was used in manufacturing for surface texture analysis, also in manufacturing for chatter detection, for quantifying weather patterns, and for stochastic bifurcation detection. Okay. So now we talked about homology. We talked about persistent homology. Let's talk about persistence optimization. All these things I showed you, all those applications did not use this. Okay, so there has been no differentiation framework for persistence until 21-22. So a lot of those applications that have been published on persistence did not leverage any differentiation whatsoever. But now we have a differentiation framework. So first, let me talk to you about persistence as a map, and then I'll show you some examples of how differentiation works. Imagine we have a point cloud that looks like this, and I'm looking at 1D persistence. If you remember, 1D persistence looks at loops, right? So you can imagine if I start doing the thickening process here, I will get a loop when I get edges between these vertices. And then when my scale parameter gets to square root 2b, I will add an edge and another edge that will look like an X, right? And then everything will fill in, right? So then I can think of this as a map B going from my point cloud to a persistence diagram that in this case will produce that point BD, okay? So I am representing that here as a map from the point cloud theta to my persistence diagram PD, okay? I can then define this function that will take my persistence diagram and produce a scalar. This is just an example. I can choose different functions V that will do this, that will take a persistence diagram and give me a number. In this case, I am computing what's called a total persistence. Total persistence basically take all the points in your persistence diagram, drop a vertical line to the diagonal, see how long that is, and add them all up. Here I have only one, so my total persistence is just this one line. Okay, but I'll show you in a little bit other options, and I'll tell you what the conditions are on this function V in order to have that differentiability framework. Now I can compose V and B, and this gives me a map from theta, the point cloud, to the scalar. Okay. So as I said, that function I showed you, the one I said is called total persistence. That's one example of something called functions of persistence. There are several options, and I'll show you some examples today. In order to, the condition of those functions is that they are local Lipschitz, and that the function is can be defined using O-minimal structures. These are two very reasonable assumptions that are used throughout in control and in engineering and science. So not restrictive. Some examples of functions that satisfy these conditions are total persistence. Here I added more points. You can see all those red lines. You add them all together, you get total persistence. Another one is called maximum persistence. I just look at the highest one. I can also look at Wasserstein distance. This is a metric that measures similarities or dissimilarities between two persistence diagrams. So I have optimal matching between the points of two persistence diagrams, and then that gives me a number that quantifies how similar they are. Okay? And it's a metric. I can also use the definition of persistent entropy, which you see here. And this gives me some measure of order in the points in my persistence diagram. And each one of these functions I can use to achieve a certain objective in what I later will show you to be optimization or minimization of some cost function. Okay. So for example, total persistence, if I promote these bars to be higher, and this is the 1D persistence diagram, then I want my point cloud to have bigger loops. I want the loops to get bigger. Okay. Maximum persistence only cares about the biggest loop. If I write an objective function where I want that bar to get higher, it means I want to take my biggest loop and make it even bigger, and so on. So this one, let me talk about this one also because we will use this one. Imagine we have a target persistence diagram, and then I have a persistence diagram that I obtained, and I want my persistence diagram to get as close as possible to my target. Then I could use this function of persistence to nudge the persistence diagram I have closer to the target persistence diagram. Okay. So now let's talk about differentiability of persistence diagram. Imagine I have this point cloud where here I have the vertices labeled, and I'm calling it theta. And imagine that at a certain value of the scale parameter, I get that loop. Now, the edge that caused that loop to appear, which I have here highlighted in red, I'm calling it B, that's called the attaching edge. That's the edge that's caused the birth of this loop. And then if I increase my scale parameter farther, I will see an edge that will pop up, and it will effectively kill that loop. All right, so now I have this loop that causes the loop to die. Okay, if you remember, I have that map now, B, that goes from my point cloud and gives me a persistence diagram. In this persistence diagram, I have this one loop here. And this is labeled now by these attaching edges. So it was born with the appearance of the attaching edge B, and it died when the attaching edge D showed up. Okay, so that's good. I haven't told you differentiation yet, right? Differentiation in here is associated with some kind of perturbation. So imagine that my point cloud here is perturbed. And in this example, I'm only perturbing that point that was P2 up there is now P2 prime. So that point is perturbed in the direction U hat. Okay. I do the same process again. I mark my attaching edge. It's now B prime, and then D prime. And now I get another persistence diagram. I'm overlaying it, where now the point is B prime, D prime. Okay. So the point that was BD when I perturbed moved to B prime, D prime. Okay.
For the clarification question, so that
Sure.
I can follow. Like, given the number of points in your point cloud, do you know how many points?
No.
Like, given the number of points, so if with perturbation, can number of points change, and is it differentiable if the number of points are changing?
Oh, so I will show you. The differentiation and persistence is a little weird because I will have a vector with the same length as many points in my persistence diagram. So each persistence diagram will get a vector. That's how my differentiation persistence diagrams will give me a set of vectors. I'm about to show you. Okay. All right. So in this example, this point moved in that direction. I only have one point. Okay. So I can define a unit vector that tells me which direction it went. And then my derivative here, this is what I was talking about. So my derivative here is this parameter Pij. So these are the vertices I have over there. And U hat is the unit vector here by which these were perturbed. I have one point in my persistence diagram here, so my derivative will just be one entry. But if I had multiple points, then for each point in my persistence diagram, after I perturb, theoretically the points will move, right? Some of them maybe won't, but if they move, I will get here entries that look like this, one per point in persistence diagram.
And with these perturbations, I think that's what I was asking, like, would the number of points change? Because then it's a bit weird, right? If you have 3 points and if you perturb, now you have 5 points in the diagram. Is it still possible to define these quantities? Or?
We have small perturbations in our point cloud here, right? All of these are small perturbations. So I should be always able to, with that in mind, I should be always able to define vectors that tell me where these points moved. Yeah.
A bifurcation situation, right? Where you have an arbitrarily small perturbation that jumps from one regime to another, and so you would have differentiation, perhaps.
Yes, but even not in differentiation persistence. If we have a system and we have a bifurcation, we usually assume we are not right at the point of a bifurcation. Yeah.
That's the general position.
Which is coming next, right? Yeah, so, well, in 2 slides. Let me show you another example. This one is for 0D. So here I have 2 points in my persistence diagram. Remember, 0D deals with connected components, right? So I go through my filtration, and this gives me this point here, right? So born at 0 and died at that value, R sigma. Now, I want to look at a range of perturbations here. Okay, so that blue region is just these 2 points are being perturbed. This is the space of perturbations. And I want to see how that maps to my persistence diagram. So if you remember, I told you 0D points in this case, when I'm talking about point clouds, they're all born at 0, and then they die, and they're all along some vertical line. So those perturbations map to some band in the vertical direction around that point red, the red point. And if I give you an example perturbation, if I make it more precise and say, imagine that my points were perturbed, now both of them, according to P1 and P, or what is it? This one here, the blue ones. So the red points are perturbed to the blue ones. Then in my persistence diagram, that corresponds to that vector going up from the red to the blue because they get farther apart, right? So they will die at a later time up. Don't worry about this Q here. I'm not going to talk about this. Okay. Let me show you another example, and there is a point behind this one. So I showed you examples where we can define our differentiation, right? And I get that vector, that set of vectors. Let me show you this example. So now I'm again showing you 4 points, and I can map those points to this persistence diagram. And now I can perturb them. In this case, I'm going to push them out diagonal, like you see. And I'm going to get my persistence diagram there, B prime, D prime. These are the values at which the birth and death occur. And then I get here, again, I have 1 point. So I have my differentiation of the persistence diagram B relative to the perturbation tilde B for the point cloud theta is given by this one entry, which in this case is 1, 1. Okay? Which should be there. All right, now this is the second example. The points now are pink. Instead of pushing them diagonally, I'm pushing them sideways. And I'm doing the same thing. You notice here the depth time is different, but the derivative is the same, 1, 1. So I have 2 different perturbations that produce the exact same derivative. So this is not unique relative to the perturbation, right? I can have 2 different perturbations that will produce the same derivative. So why does that happen? That happened because this assumption was violated in the example I showed you. So this is the general position criteria, and it has 2 conditions in order for my derivative to be unique relative to the perturbations. And one of them is that I cannot have 2 points on top of each other, my point cloud. And I cannot have a pair of points that are equidistant, okay? And this may seem like a limiting assumption, but in actual data, it's hard for this assumption to be satisfied, A. And B, we have, even if this causes any division by 0 errors, we can always perturb the data by noise, add a small amount of noise, and this breaks these equalities. So we have not found these to be restricting. The optimizer was able to proceed through the calculation, and we had no issues. Okay. All right. So now I have these, I define the differentiation of persistence, and I have that map that takes me to a scalar. So this enables us, the combination of these things, the definition of a loss function and definition of differentiation, allows us now to use algorithms like gradient descent to try to optimize, find minima of our objective function. So here is an example where I write this loss function here, and this one is promoting the total persistence, and I have the second term here that will keep the points bounded. So let me show you how this works in action. I start with a loop, and I apply gradient descent, and I am trying to make my loop big. Here there is only one, so it's just trying to promote a bigger loop. And then this term here is keeping it within this box. And you see here the loss starts up there, and it comes down, and then it settles. So I am doing that via the persistence diagram. I'm specifying constraints here that's driving this, okay? Here's another example where I have the same starting point cloud in the top and the bottom, and I am specifying similar constraints. The first three are the same for both. So expanding loops, I want to expand my loops. I have a lifetime restriction. So now I added this wall here in my persistence diagram where I don't want my points to go above that. And I have that regularization term. But the difference in the bottom one here is that now I want to minimize entropy. So let me show you the effect of this. The video will flip back so you can see it from the beginning. So remember, we started from the same initial condition for the point cloud. And so what happened here, when I don't have the minimized entropy condition in the top, it maximized the loops, but I have more loops. Here, I asked it to minimize entropy in the persistence. And so what it did, it maximized the loops, but it gave me fewer ones. It gave me a simpler configuration. Okay, so here you can watch it from the beginning, how these loops start forming, how these points start moving, and then they don't go above this. And you can see how the loss function is converging.
For us, the second case,
The bottom
you're
one?
maximizing the loop size, but also minimizing entropy. Which one are you optimizing there, and which one is a constraint?
For this one?
Yeah,
All of them.
they're all.
This one here, I have two conditions. I can add them up, right? I can add my
You're
conditions.
just adding them and.
Yes,
adding it
yes,
to-
yes.
Okay.
Yes, I'm building my loss function.
I missed that. Okay.
Yeah, I have these small, the functions of persistence I showed you. I can use them individually or I can combine them. So here I added another constraint to another term in my
I see.
loss function.
Just to follow up on this question, if you were to only have a loss function for expand loops, that would just go to the outer edges, one loop. If I minimize entropy, it all just collapses to a single point. Is that, and this is somehow the bottom one is trying to like go in between those two solutions.
I mean, I think this one will not go all the way to a point. It will not collapse to a point.
Minimizing entropy will reduce to a single
But not to a point.
point in the persistence diagram.
Yes,
Yeah.
yes.
So
Problem's non-convex, right? These are just local optimal that you're showing. You just start from some initial condition and this is what it converges to, but if you start from some other initial condition, you would get, if you start from some different point cloud, you would get.
Yes, it might go somewhere else. We are trying to drive. I'll show why, because here there are some nice conditions we can specify here that will simplify getting what you want there.
So you're just using gradient descent to do the optimizations.
Yes, yes. But my loss function has topological terms. Okay. This is the one where I have a target persistence diagram. So the green one is target, the red one is some starting point cloud that we have, or the persistence diagram that corresponds to a starting point cloud. And now I'm using the Wasserstein distance. So I'm trying to minimize that distance between the two. And so I'm driving the current point cloud to some target point cloud. Here I have no, so you see that this point is converging to that point. This is important because I will show you later, part of the data assimilation, I have two persistence diagrams coming from two different things, a model and measurements, and I'm trying to make my model get closer to the measurements. So this example is relevant to that, okay? All right. This one, I have some noise in my target persistence diagram. The other one, I didn't have that. And you can see that using the Wasserstein distance, my current persistence diagram is approaching my target, but it's not concerning itself much with matching these points close to the diagonal. So it is trying to get close and get as close as possible to the prominent features, because remember here, the assumption was that the points near the diagonal are noise, okay? And I care about the ones far from the diagonal. So while it doesn't overlap with it, like in the other example, it still gets close to it, and it doesn't try to match the noise pieces. So that's nice because then if I have noise in my targets, I don't have to worry about that. It doesn't try to match those. Okay. So now we talked about persistent homology, persistence optimization. Let's talk about time series forecasting because we're going to collect all those pieces and put them together. This is just the general outline for time series forecasting. We start with some time series. We have a window x sub p. So I have a subset of those points. So I have my window over those. And using the points in that window, I'm trying to predict the next point. So I take that window and I feed it through some function, some forecast function g. This is just a cartoon of just one example. It's like a recurrent neural net, but it doesn't have to be that. Okay, so that function, your forecast function, takes the window x sub p. It takes some weights that you're going to be trying to compute, and it takes some parameter mu, some internal parameters that you're not trying to optimize. These stay fixed, and I'll show you some examples. And then using that knowledge, I produce a new point at tn plus 1. And now I have a new point, so I can repeat the process. I slide my window over, and I keep forecasting. Okay. Some of the existing tools to do this are autoregressive, moving average, and I can combine them both for what people call the ARMA. So I combine both, and in both cases, these are the coefficients I'm trying to compute. So I'm assuming, for example, in this case, I'm assuming this is my model. These are some residuals, and I'm trying to find what these phi i's are. Same thing here, I'm trying to find what the theta i's are. And when I combine them, I'm trying to find both. Okay. So I'm trying to find the coefficients that best fit my data or produce the best forecasts. Okay. Mu there is the average of the window. All right. So that's the one approach. That approach has been established for a long time. Another approach to define the forecasting function, so we have options, right? I'm showing you these options, is using random feature maps forecasting. So this one, I have some unknown system, and all I have from that system are noisy observations. This is the measurement covariance matrix, and this is some noise, and this is the true state, okay? And UNO is just the observation, the noisy observation. So my system lives in some dimension D, or my observations too live in some dimension D. And in random feature maps, I take my observations and I project them. I do random projections into a higher dimensional space. So in this case, the dimension of the space is dr. Wn and Bn. So Wn is a matrix that's sampled uniformly. Bn is a bias vector that's also sampled uniformly. And tanh is just the hyperbolic tangent function. So this gives me a family of functions. And the universal approximation theorem tells me that I can approximate any continuous function to any arbitrary accuracy using that family. Okay, but it doesn't tell you how. So it doesn't tell you what the activation function that tanh, that one works. That's a very popular choice, but doesn't tell you if there is other better options for non-polynomial activation functions. And it doesn't tell you how to select your Wn and Bn. It just tells you some approximation exists that will be dense in the space of functions. So you have to make choices there, but then you project, and after you project, your Wn and Bn do not change. It's not something we are optimizing. Okay. So then that puts you in a space that is of dimension dr. Then from that dimension dr, I take those vectors, and I have this matrix. I have this transformation that brings me down to dimension D. So this gives me here a surrogate model. This is the matrix of weights that I'm trying to find. Okay, this is and I use linear regression to get the weights. Then having the surrogate model in hand, I can propagate. I can forecast the next point. Okay, and here I am showing you the loss function, which tries to minimize the difference between my model and my measurements. And this is just a regularization term. Okay. So some issues, some limitations of this approach is that the parameter tuning there is sometimes tricky. You need to experiment with ranges to sample from. And the other one is that many times random feature maps forecasting assumes that you know the noise statistics. and that the noise is Gaussian. And these are tricky assumptions, not always satisfied. Yes?
Second term of your loss function is just Frobenius norm W.
I'm sorry, say again?
The second term on your loss function is just Frobenius norm on W. Is that just necessary to sort of regularize the problem, or is there
Yes.
something? Okay.
It's just regularization. Yeah. Yeah. All right. This is just another example that fits within that G forecasting function I showed you earlier. I just wanted to stress that. And here, so these are the ones that I am trying to compute, the weights I'm trying to compute. Wn and Dn, as I said, are not things I am trying to optimize. So those go under that the mu category here. These are the parameters, internal parameters that don't change. Okay, but Wn are these WLRs I'm trying to compute. So it's all in the same spirit of that forecast function I introduced earlier. Let me show you an example for random feature map. So this is a method that's established in literature, but I want to show you some of the results. I'm going to show you how it works on Lorentz system. So I have this Lorentz system, and these are the chaotic parameters. This is what I chose to do the random feature map forecasting. So this is the reservoir dimension dr, and this is how I sampled those matrices, Wn and the bias vector, okay, uniformly. All right. So you can see here in the video, we collect data here, and then when the green line is drawn, that's when I have my model, and my model now is trying to predict. Okay. So I train on the data before the green line. Now after the green line, I have the forecast, and I have the ground truth. And you can see here, I don't have noise here. This is just a chaotic system, but you can see here that they start diverging, right? Because I train my model, I let it go. It's a chaotic system. After a while, I'm going to lose accuracy. Okay. I'm not incorporating information from my new measurements in this example. Okay. Another example of forecast function is the long short-term memory network. And in this network, the input is the current state and the so I input my current state, and this has a long-term and short-term memory gates in it. We have a forget gate that moves data from the short-term to the long-term memory, and we have the main layer and input gates and output gates. I'm not going to talk about it, but all I'm going to say here is that all this does, you give it input data, and it outputs out some forecasts for you. And there is some parameters you can set here, but I will show you how in our forecast, when we use this, we don't worry too much about tuning those parameters, and we just take the default. We don't do lots of tuning, and I show you how the results converge eventually, which is an advantage. You don't have to work as hard here to tune your parameters. Okay. This one also fits within this framework for this function G. Okay. So now let's see how we can put all of this together in a data assimilation framework. So here is our model. And our model can produce some estimates or forecasts for our variable. Okay. Then I get some incoming measurements. And the ground truth lies somewhere within the measurements, we would hope, right? The measurement is getting us closer to the ground truth, but I don't have access to that. And so I would like to be able to take the measurements. And this is a term that computes the differences between the measurement and the model. K is some gain matrix that you can tune in order to get your estimation closer to the measurement and hopefully the ground truth. And here I show you how I do this update in 3 steps. Of course, you can, if you sample faster, if your measurement is sampled faster, this curve will become smoother, right? Because I'm doing my updates in less discrete way than I'm showing you here. But this is the idea of data assimilation. Data assimilation, many times there is the Gaussian noise assumption as well. And having to know the noise statistics. So in order to mitigate some of these and introduce a flexible way of specifying the terms in your cost function, we combine those persistence differentiation with data assimilation, and we came up with this approach called topological approach for data assimilation. And after much thought, we called it TADA. That was actually Max's idea. So in this framework, you will see that it parallels a lot of the things I've shown you before. We have some measurements, we have some assimilation windows, so we have a forecast model, and it can be one of the ones I showed you or any of your other favorite forecasting functions, as long as it fits within that framework. And here we are trying to figure out what that WN, those weights, should be in order to make our forecasts more accurate. Our measurements produce some point cloud that we can compute a persistence diagram from, right? That's the green one. And then our forecast model can also produce a point cloud. So that gives me that second persistence diagram. And I can use Wasserstein distance to nudge my model persistence diagram closer to the measurement diagram. I did tell you this is coming, right? So now if I minimize that, the hope is that the next point will be closer to the ground truth. The next forecasted point will be closer to the ground truth. And then I keep repeating this. So I forecast, collect measurements, nudge it closer, and I keep sliding the assimilation window. And at the end, we have this optimized model with these optimized weights W hat. Okay. Now, one issue that we encountered with this is that if you remember, I was showing you point clouds. So you go from a time series with time index points to a point cloud. When you do that, you lose temporal information. So the first time we were trying to do this, we would get the measurement time series, for example, and the model will look similar to it, but they will be shifted from each other. And so instead, what we do, we take the difference between the 2 point clouds and we compute the persistence diagram on that. And then we measure, in our Wasserstein distance, we take the distance between the persistence diagram of the residuals and the empty persistence diagram. Because ideally, if they're exactly the same, you will have just the diagonal. You'll have empty, right? You'll have nothing there. Okay, your persistence diagram for the residuals. The other issue, so that gives us a term here, J1. And the other thing, which is related to the question I got earlier, I believe, we don't want, as we are going through this process, we don't want our model to change too much. We don't want these big jumps. And so the other thing we did, we would sample randomly from the training data and compute residuals, and also compute this second term over here, J2. So the combination of both, one of them made sure that the forecasts and the measurements were locked temporally, and the other one made sure that things aren't jumping around too much and I'm not converging. And we found that the combination of these two helped us get better forecasts. Let me show you just a snapshot of one TADA update step. So imagine here I have my model, I have my measurements, and they're starting to deviate. I go to my TADA step. I compute the Wasserstein distance the way I described. And then I come up with another, I update my model weights, and now this brings them closer to each other. So now my model and my measurements are more aligned. So this is just a snapshot of one window of how this works. Okay. So what I've been showing you is just the pieces of the approach and some toy examples or snapshots of one update window. This one shows you how, when we put it all together, what happens. So this is the Lorenz example. Excuse me, the points in green are my windows sliding across. And you see my measurements that stay stationary, the blue ones, that's the ground truth. And red is what my model is giving me. And you can see that my model is off, especially the points that are far temporally. But as the sliding window gets closer and I keep updating my model, at the end, I get pretty good match. The points ahead of my window are pretty good. But the ones far keep getting closer as my window incorporates new measurements and updates my weights. So that's the time series view, and this is the state space view. Okay. So there are some parameters we need to talk about here in the approach, and this is common to data assimilation in general. So we have the learning rate dependence. That's the size of step you take when you're computing your, when you're trying to minimize, when you're trying to find your minima of your cost function. Okay. So, and the other one I want to talk about, the times I'm going to show you here, these are Lyapunov times. So the maximum Lyapunov exponent of Lorentz times time. I'm showing the time in terms of that product. And I'm measuring accuracy according to this quantity here. Okay, so I have the difference between the model and what I know is true, the relative error. And if this relative error exceeds 5%, that's when I say my forecast is no longer good. Okay. All right. Notice here that I have j equal j1. So here I am just using the persistence diagram of the residuals. I am not sampling randomly. I want to show you here why we do that. So on the left, you see the mean forecast time. And on the right, well, my right, you know what I mean. Your left is the mean, and your right is the standard deviation, okay? And I'm trying to choose those parameters for my data assimilation. I want the decay rate, I want my decay rate, and I want my learning rate. Okay, so ideally, I want my forecast time to be long. So I would like to pick regions, combinations of these parameters, where I have light green, right? And I don't want that region to be narrow. What you see here is that if I don't have that second term, the region where I get to pick those parameters is quite narrow. So it's sensitive to the combination of those parameters. It's not as forgiving. When I add that second term, J2, so I'm sampling randomly from the training set, and I am adding that second J2 for the residuals from that, that band gets much bigger. So now it is more forgiving. I can pick parameters here, and my data assimilation will give me long forecast times. Okay. Here is a picture that shows the learning rate dependence. So red is TADA and blue is linear regression. And you see here that for these, so I see these peaks that go up that maximize my forecast time for these two values of learning rate. And I'm going to show you results for both to see, what's the influence if I pick one versus the other. But this one shows us the effect of the window size. Because remember, I have a window sliding across, right? And how big does that window need to be? And what this plot shows us is that the method is not sensitive to the window size, which is good. Because persistence scales, the computations of persistence scale with the number of simplices, which if I have a bigger point cloud, I potentially will have to spend more time computing it. So if I can do this on smaller windows, that's better, right? So this gives us that freedom. Yeah?
The window size here.
I'm sorry?
On the window size.
Oh, yeah.
Imagine there's situations where window size would definitely be better. Like if you have, stochastic processes that have noise and you have to sort of have enough data in your window for all the noise effects to kind of average out. I mean, are you drawing conclusions that are broad based on this, or is this just for a certain class of problems?
This is for the classes we tested. But we're always, if you're predicting just one point and you're then adjusting, right? It depends also how fast you're updating. I think if you're not updating as frequently, I agree with what you said. You have to be careful about it. But for the cases we tested, it did not make a big difference for us. Okay. Now I'm going to show you the noise robustness. So these two diagrams are for white noise. And the top one is for learning rate 10 minus 6. The bottom one is for learning rate 10 minus 5. And these ones, I'm just going to show you all of them. The middle one is pink, and this one is brown. So pink and brown are cases where classical data assimilation methods do not apply because it doesn't have the Gaussian noise assumption. One curious thing we noticed here is that persistence, and this we saw this in other papers too, or in other work. It gives you better performance for these kinds of noises, and we don't know why. So sometimes adding noise, the other interesting one is that if you have data and you add noise and you do persistence, you get better results. And this one is showing us that sometimes for pink and brown noise, you get better forecasting times than white. So if someone has ideas on why this happens, we are open. We don't know why it happens. Okay. All right, so that was for Lorentz system. We wanted to see how this works if I have a higher dimensional system. So we did this for Lorentz 96. And these are the parameter values that we used. Okay. This is a heat map that shows the forecast time. And this is a video, so it should show you. So we start with some, as we slide across and we see that this is the error, sorry, not the forecast time, yeah. So this is the error, it's going down. I'm like, why is it going, this is not good. This is the error, we want it down, not the forecast time. All right, so you see that the error is going down, which is great. So it's dropping down, and that's what we would like to see. So it works for the Lorentz 96 system as well. Okay. All right, so these were some numerical examples that we studied, and Max did an internship this past summer at the Air Force Lab in California, and there they like to think about Hall effect thrusters. Okay, so in Hall effect thrusters, we have these heavy ions that are being ejected and producing thrust. These are solar panels. This is an electric thruster. And these are very complicated systems. There is a lot of elements interacting, and one of them is, you have the power coming in, but the ions sometimes hit the solar panels, so they affect that. So you have these connected elements and these feedback cycles. And so these are difficult to simulate. There are certain simulations, and Max got some results. The results I will show you is for a simulation that does things on a particle level. So it looks at multi-scale interactions of particles to simulate the behavior of these thrusters. Okay. This data is declassified, so we can show it. Okay, so this is what the data looks like. It's not on a normal rectangular grid, but it is symmetric, so we can consider half of the domain. And if you look at that, it looks something like this. This is for electron temperature. We have data for also other states of the Hall effect thruster. I will be talking about two. One of them is the temperature. So it looks like this if you plot it over time. And the other one is the electric potential. If I take the data and unfold it, so this shows both spatial and temporal, the data on spatial and temporal unfolding looks like this for the temperature and the potential. So let's start with the electron temperature results. So do you see our starting condition? We have some forecast error, but then as we incorporate more and more windows into our approach, the error, this is the error, the squared error also goes down, which is good at all the locations. And if you want to see a time series representation, this is dimension here is some spatial locations that I picked. You see how I start from some initial model, initial value for my model, and then the forecast gets better and better and locks in with the measurements. So we were happy to see that. The electric potential, this one had outliers in it. The temperature data was a little smoother. So we were able to take it and do the data assimilation on it. We ran into difficulties with the electric potential because if you look at this here, I have a lot of variance in the measurements. And so we tried moving average smoothing. And I think N is the, how many standard deviations the window size was?
It's on either side.
How many points on either side, yes. And so you see here that for 3, the data became a little less varied, variance went down, and that gave us the best forecasting results. So we needed to do data smoothing when we had the outliers. Right, so this is the starting, and you see again that the error goes down. And these are the time series. And look at this. The forecast, we were lazy here. We didn't worry too much about having a forecast that's initially close. This is the LSTM. All of these results are for the LSTM, and we didn't worry about tuning those parameters. So start the data assimilation, and then it brings the forecast closer to the measurements. So here, these are the 2 publications related to this work. The second one will be on the archive soon. We get the green light from the Air Force lab researchers to put it on the archive. Okay. All right. That's the whole story. So we have a lot of the things. So some of the things I showed you are already on this package teaspoon. And Max will be pushing the rest of the functions into this Python package where we do all these topological signal processing work. And there is a mini tutorial. So the slides and the Jupyter notebooks are all available here. If you want to get into this, you don't know where to start, you can go to that website and you can work through it, install Teaspoon, and let us know what you think. Raise issues on GitHub. And we welcome contributors and opinions. Thank you so much.
Time for questions.
Yes.
When you, there's a piece here that I'm not getting, and that when you talk about forecasting for your examples,
Yes.
the noise is a measurement noise, right? The
Yes.
noise in the measurements, but it's not noise in process.
Correct.
So, and that's why you're able to, once you get a good forecast, it stays good. Right?
Well, I keep updating the weights.
Yeah.
It won't stay good.
So I mean, but the horizon over which it's good stays is pretty long, right? So are you
No,
always-
not
you're
no.
always forecasting one step ahead, but then you use that to forecast a second step.
But every time I get measurement, I update my weights.
So you're
Otherwise,
in all of your examples on forecasting, then it's basically restricted to one step ahead forecasts. Is that right?
I think we do 1-step forecasts. Yeah, yeah. If you,
That was a piece I was missing. I was thinking
Yeah.
you were going multiple steps ahead.
it depends on the frequency of updates here, because in the numerical examples we have, we were updating a step at a time. But if you don't, then you can't. But you can always nudge yourself
Because
closer.
the reason I was asking is that I mean, ultimately, you expect if you go far enough away from the present time, your forecast is always going to get arbitrarily bad.
Will get bad, yeah, for these chaotic systems, yeah.
Well, even for non-chaotic systems with process noise, that would.
If it has noise, yes.
Right.
I was trying to get to the slide that shows how bad it gets if you don't update.
Questions? Good discussion during the seminar. So perhaps we should thank the speaker and.
Thank you.
Yeah.
He makes it a punchline.
Yeah. That's my weekend plan.
Yeah, for you, yeah. Actually, made it
Yeah,
You're gonna be in the
Yeah, all for the Lorenz system, I was using a window size of 50. You can make it more efficient with a smaller window because you're. You're allowed me to go out that way. I was getting about 1 second.
Okay. You're gonna go here, like basically 80 back.
No, I was doing it on my workstation computer, yeah.
yes. I heard he just took this, like,
I'm actually.
Trump said he could retire in 6 years. Yeah, that's what I heard.
I was wondering.
I mean, I've been working with Shane Ross.
No, I heard he took this deal, not the deal with all. At his age, he's smart.
See, the thing is, I'm always like you never liked me. So I found
Yeah.
Of
course, we secretly talk more about some of that. A lot of the
ways of being.
Yeah, I am like, maybe he will give me a frontier one day, so that was my thing. Now I am like, okay, he's gone, I will never get a frontier.
You really, okay.
Yeah. I mean,
I don't know.
Because like there's something in it. Like, I don't know.
Yeah, DC had one when I just started, and DC running so smoothly. Like, watching how DC did it, I'm like, okay, I can just mimic this. That would be my strategy.
Yeah. I guess, I overestimated the amount of time to do those frontier projects, and they are really good. Yeah, Pico, she got it.
Yeah.
Seems like. So maybe I'm being, and that's really negative about it. It's just whenever it's that much money. They're gonna like breathe down your neck to get things done. If there's this desire, it doesn't change too much. That's quite accurate.
I think I would be comfortable going in with Corman. I don't know if like, it also depends on the person.
Scared to death every single time I met him.
He's an interesting guy.
I've only just one conversation with him. And he was yelling. You've been like, during that conversation. It's like, that's my experience. I hope he enjoys fishing.
Yeah, well.
For us, nice talk.
Thank you. You guys have an engineering are twice as big as those ones we have in you guys are rich enough to have those big cookies.
I don't know.